All right, so in this video, we're going to talk about Chapter 2, Section 6. As you can see, this is about differentials. Specifically, we're going to just add on some more details here, everything we've learned so far. So, show you what I'm talking about. Like always, we're going to go over a handful of slides, a couple problems at the end, and then make sure you're good with the homework here. So, a little reminder, we learned about the derivative, the definition of a derivative. The first thing we learned, the derivative is the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, and we did that a couple videos ago. We learned how to do this, and then we had sort of the shortcuts the last video. So, we're going to expand on that today. All right, so now we're going to deal with this idea of an increment. And you see here, I didn't really talk about it. Let me go back one piece here. Increment notation allows interpreting the numerator and the denominator of the difference quotient separately. Okay, what that means is, we'll talk about this. We have a function here, f of x equals x to the third, or y equals x to the third. We have a change in x, so the x is going to change. It's going to go from 2 to 2.1, and it means we're going to have a y value that changes also. So if you were to plug in f of 2, the original number, into this formula, we get 8. 2 to the third is 8. You plug in 2.1, it's going to be slightly larger. And just to make sure we're all clear here, remember, you can always use your calculator for this. So don't be afraid to, if you're not sure where are they getting this 2.1 from, remember, it's just 2.1 times 2.1 times 2.1. And you see, this is how they get this 9.261. Okay, just to make sure you're on board with that. Okay, so the change in x, and they call this the increment of x, is denoted by this delta x. Now that triangle right there is your Greek letter delta, so delta x is going to be your change of x. You might have seen that in the past before. Okay, so Greek letter delta, anytime you see that, in the future it's going to be the change, or in this case, the difference of something. The change in y, of course, is denoted by delta y. Same kind of thing. So if you look at it, the change of x is, look at the two x's that you had, the start and the finish. You started at 2, you ended at 2.1. The change, the amount that you went over, is 0.1. And then same thing for the delta y, you want to get the two y values. So you plug in the 2.1 into the function. You plug in the 2.2, you subtract those values, and that's your change there. Very similar to when we find the slope of an equation, we're looking for the change of y over the change of x. It's the same kind of changes here that we're talking about. So that's what you see here at the bottom. This is sort of the change in y, this is the change of x, and this is where you end up with a basically similar formula to what we're talking about right here. So h that we've dealt with before, this is going to be replaced, not replaced, but for this part, we're going to call that delta x. So if you look at the two formulas here, they're exactly the same. We have some sort of an x value, and we plug that into both functions, and then the difference is, minus these two x values, it's that delta x. It's that gap between x's. So this is what we're going to get over here on top. So it's a very similar formula that you've had. So a couple things. Delta x is going to be the difference of the two x's. So if you solve for the second x, it's basically the first x plus delta x. That little change is added to x, the first x. That's how you get the delta x. Delta y, same kind of things. You subtract these, and that's how you get this top part, this change in the two x's. So instead of saying f of x2 minus f of x1, or y2 minus y1, we replace that x2 with this right here, what we solved for, and that's why it's f of x1 plus delta x minus f of x1. So, in the picture, in the graph, how you can kind of see it here, like I was saying before, it's like your slope. When you look at the two changes, here's your delta x, it's the gap between the two x values. So we have 2 points we're focusing on. The delta x is the difference between their x's, the delta y is the difference between the two y's, just like that. And if you were to divide them one over another, remember, that's giving you that secant line right there. That would be your slope. That would be the delta y over delta x. Nothing really new. Something you've dealt with way in the past, and then again recently, this idea of the slope of a line. Okay, so a couple important things. Your delta x can either be positive or negative. This was represented by the change in y corresponding to a delta x change in x. So just like you can have slopes that go up and down, you can have changes that go up and down. Same kind of thing. Whatever your first point is, and what it right here, and whatever your second point is, you take those two and you plug them in, and that's how you're going to get your delta x and your delta y. Okay, so like I mentioned, it gives you the slope of that secant line that connects those 2 points right there. All right, now we have a function here. We want to find delta x, delta y, and then delta y over delta x for the first x is 1, the second x is 2. All right, so the first one, the easy one. To get delta x, we just subtract x2 minus x1. That's a 2 minus 1. There is a 1. Not so bad. Delta y, a little bit different, but remember, we plug in, find the function, find the y value of the second x, this 2. So we get f of 2, we get a 4 over 2, which is a 2, and then we subtract f of 1, which is 1/2, so we get 2 minus 1/2, or 4/2 minus 1/2. Either way, our delta y is going to be a 3/2 here. And then the third thing they wanted you to find was the delta y over the delta x. Delta y over delta x is all the same formula. y2 minus y1, or f of x2 minus f of x1. And we get this 3/2 over the 1, which is simply reduced down to 3/2. So 3 different things they're going to want you to find. Yes, they're all tied together here. Okay, so now they want us to find this and realize this is no different than this delta y delta x over here. We have a different function though. So they give us our first 2 x values, or sorry, they give us the first x value, and they give us the delta x. So there's a little bit different here. So watch how we do this. We're going to plug everything in, and you see here, x plus delta x is basically x1 plus the delta x. Remember, go back a couple slides, right? Is it right here? Your second x value is basically the first x value plus that delta x, that gap, that change. So right here, this f of x plus x1 plus delta x is f of x2 minus f of x1, and then we have a delta x in the bottom. So these are exactly the same, just showing you 2 different things here. Now we start plugging things in here. And the trick is you're going to have, it looks like not many variables, but there's lots of different things. X is a variable, x1, x2, y1, y2, delta x, delta y, f of x1, f of x2. There's so many things out there. So you can't just start throwing numbers in and substituting. You have to make sure you've got the right pieces. So here they tell you x1 is 1, so that's why there's a 1 right here and right here for these 2. They tell you delta x is 2, so I replace that delta x with a 2 and this delta x with a 2. And that's how they arrive here at this current place where we are. We're not done yet, but we're just on the way. Okay, so now that is the same as finding f of 3 minus f of 1. So always go back to your original equation, your function. When I find f of 3, I get 9 over 2. That's that part right there. Minus f of 1, that's 1/2 right there, divided by 2. So we get, on the top, we get an 8/2, which is a 4. 4 over 2 is a 2. And that's our answer right here. And remember, that is basically the slope of the secant line connecting the 2 dots. Now what they don't have here, just kind of add a little extra detail on this. This is kind of how your graph looks. They tell you they want you to find x1 right here. But they don't tell you anything else except for the delta x, this little gap right here, that's 2. That length right here is 2. Let me make it a little further. So now you have to kind of figure out, oh yeah, that means 3. Then you go find f of 1, you go find f of 3, and then if you were to connect those 2 dots of that equation, those 2 dots, that secant line will have a slope of 2 that we found right here. So not only do I want you to know how to do this, I want you to have an idea and understanding of what it is you're finding. You're not just machines plugging in numbers, you have to understand what it is you're solving or figuring out in each of these cases. Okay, so now they're saying pretend that the limit of the derivative, okay, I don't know if that should have had limit there twice, but just assume that it exists, okay? For a very small delta x, they want to find the derivative. Okay, so sorry, not they want to find, giving you a fact here. When delta x is very, very small, this is about what the derivative is, okay? Now as delta x gets very big, things are different, but this goes back to our definition. Now I'm going to go back one more time to the very first slide of the day. Okay, right there. Remember, this is when the bottom is getting closer and closer to 0. That's what they mean by delta x is very small. So as h is closer and closer to 0, this is the definition of the derivative. So remember, we replaced the h with the delta x. So for this fact right here, this is a formula for the derivative. And remember, this is true as long as your delta x is very tiny. Okay, approaching 0 essentially. And then we have this other fact. This, all it is I'm multiplying both sides by delta x. So delta y is pretty much the same as delta x times the derivative. Now we're going to use all this stuff here in a second. So we have the differential dy equals f prime of x times delta x, or d of f, the differential, equals f prime of x times delta x. So a couple different notations that you're going to see in a second how we use those. So when we're talking about this dy or the df, this is known as the differential. All right, and it's the product, as you see here. It's multiplying your derivative times dx. All right, so let's plug some stuff in here and see what we have. So there's going to be a lot of different things they're going to throw at you. So I'm going to try to keep this as gentle as I can, not give you too much here. All right, so here's what's going on. All right, let me see what we have here. This is kind of like, not exactly the last one, but it's similar. If you have 2 points, you have an x right here, and then you have some change, some delta x right here. We're going to add that on, so we're going to get 2 different points on the function. We already know that we can find the secant line between them, and then we can find the slope of that just because we know enough about the points. What we've done before is we've found the derivative, which gives you the slope of this red line right here. And remember, this red line is your tangent line. It's only touching 1 point. And the secant line, as this point gets closer and closer to the original point, meaning as delta x gets smaller and smaller, this green line gets closer and closer to the red one. All right? And that's why we're able to kind of come up with a formula for that. So the tangent line has a slope of the derivative with a horizontal change of dx. The vertical change is dy. All right, lots of interesting things here, but this picture does kind of sum up everything very well. This is the key point, this x, this first point down here. So if I'm looking at some delta x, some change, and I'm moving over to get a second point, that's my delta x. It's exactly the same as this dx that we're talking about, okay? But what differs is over here. Delta y is the actual value of the point, how far we are over, whereas dy is going by what the tangent line is, because there's no second point. It's what we want it to, what we're trying to ultimately find out. Okay, so I'm going to tell you, this picture is a good one to refer back to. I'm going to keep coming back to this as we do other problems, because this sort of helps explain what are we looking for, because they're going to have you find dy. They're going to have you find delta y, and I'll admit, it's very easy to mix them up, or at some point it's like, what's the difference? Here's the difference, okay? If you have 2 points, the secant line, the difference between those two is delta y and delta x. If you don't have this second point, and you're just dealing with a tangent line, your delta x and dx are the same, but the dy is what goes, just think the dy and the dx go to the tangent line. The delta x, the delta y, they go to the secant line. Okay, and like I said, I'm going to bounce back to this number of times. So delta x, dx both represent change of x because they're the same. The delta y is the actual change, whereas the dy is sort of the guesstimated one, what they expect it to be. So the approximate change in y, dealing with the derivative. Now I'm going to be honest and tell you, as time goes on, we care about this one, the derivative, a lot more than the actual change, because that's going to be able to model everything for us. But when it comes to these certain applications, you want to know what actually did change, not what was projected or what we assume it's going to be. Okay, so in the applications, we're going to use dy to estimate delta y and all that good stuff. So here's our first problem. Find dy for this function and evaluate dy for x equals 2 and dx equals 0.1. So we have this formula that we did earlier. Remember, dy equals f prime of x delta x, or dx, sorry. So we know the derivative is 2x plus 3. Now let me stop, pause your video, make sure you're clear how that is there. This is something we knew from the last video before, how to find the derivative of f prime of x. Remember, multiply the power down, so we get a 2x. The x drops away, so we get a 2x plus 3. That's the derivative. So dy, and I don't like how they kind of get lazy and don't write this, but this is dy. dy equals 2x plus 3 in a parenthesis times dx. So for x equals 2 and dx equals 0.1, you just plug those right into this formula. So you get 2 times 2 plus 3 times 0.1, and that's how you get a dy of 0.7. Okay? So that's going to tell you the dy. Now let's go back and look at this picture. Remember this one right here? The dy, remember, is the change in terms of the derivative, the tangent line. This red line is your tangent line. All right, so that's all they're asking us to find. What's that change right there? Okay, so now we have a little different ask. They want us to find delta y and dy when x equals 2. Okay, so let's go back to some other formulas. Remember, delta y, we learned that a couple slides back, was f of some x value, in this case it's going to be f of 2, plus the delta x minus the f of 2. Okay, one of our early slides today. X plus delta x minus f of x, that's what we're doing. We know the x value is 2. We don't know the delta x. We don't know the delta y. That's what we're trying to find. Okay, so we start plugging things in here, and you look at what we get. Okay, now, make sure you remember how to do this. What are they asking here? So let me start with this back end, f of 2. I plug in 2 to this formula, I get 12 minus 4. That's what this second parenthesis is. All of this becomes this. And of course, there's a minus in front. Then all of this is that right there. Remember, we're plugging 2 plus delta x into every x of my original function. So that's why it's 6 times 2 plus delta x minus parenthesis 2 plus delta x squared. Now in the next step, kind of follow what's going on here. We are distributing, we are foiling, we're distributing a negative. All kinds of things happen. So make sure you see that right there. Okay, so now clean up this stuff a little bit, and we end up getting this. So notice the 12's canceled, the negative 4 and the 4 canceled, kind of like we were doing in previous problems last week. And then these two are similar terms. Yeah, it's a weird delta x, but they're still the same variable. So we have 6 of them minus 4 of them. That's how we get 2 of them right here. And then, of course, you have a minus delta x squared. So this is what we get for delta y, and that's as far as we're going to go on that first one right there. Okay. Now they bring up a couple facts here. You can kind of plug everything in here. And then they say dy equals the derivative times dx. Okay, so remember we've had this before, so little review. That's your derivative from this, and we know f prime of 2 is 2. So remember this other formula. I'll put it over here. dy equals f prime of x times dx. Okay, so we went and found the derivative, which is this. We plugged in 2 to that, and that's how we got a 2. There's a lot of 2's floating around, but I want to make sure you're clear. This is the derivative from our shortcut that we did, and then you plug in 2 to this formula, and you get 6 minus 4, which is 2. So that's how we get a 2 times delta x, and they remind us, of this old fact that dx is the same as delta x. Those are interchangeable. The dy and the delta y are not the same, but the dy and the the dy and the delta y are going to be different. The dx and the delta x, those are going to be the same. We're going to substitute one for another whenever we need in those. It's the dy and the delta y that will vary, and they will be different because one's the actual change of y, one of them is the approximate change in y. Okay, so what's not fulfilling on these is you don't really have any more of an answer. This is it. For each of these, this is delta y. This is, oops, sorry, not all that, just that right there, that's the dy. Okay, so let's go a little further. So part B, we're going to find delta y and dy from part A, and they're going to give us various delta x's. So looking at these two things that we just found, this right here and this right here. Okay, so I'll just put it up on the top here. Delta y equals 2 delta x minus delta x squared. And then dy equals 2 delta x. Okay, so they're saying use the stuff from the first one. And now we want to know what's delta y and dy given that we have these different delta x values. Okay, so treat this like three different problems. I'm going to take this 0.1, I'm going to plug it into here, that's going to give me the dy. I'm going to take the 0.1 and plug it into here and here, that's going to give me the delta y. So that's what they're doing here. And they plug these in here on the table, which doesn't exactly tell us everything, that's why I want to write a little bit extra, but just look at this delta y right here. So delta y gives you 2 times the 0.1 minus the 0.1 squared, and this is how we're getting the delta y. We get a 0.2 and minus 0.1 squared, which is 0.01, and that's how they got delta y equals 0.19. That right there. Now whereas dy, when I plug in the 0.1, remember this is they're giving us this right here. So I take 2 times 0.1, and you see we get a 0.2. Now, I'm going to go back. Now, I can do this. I don't need to show you this. I assume you guys will have no problem plugging 0.2 into this and then plugging 0.1 into this. And, oh, sorry, 0.1, 0.2, 0.3. You just do the same exact work here. Okay, so that's how they completed or they filled out this table. So look that over for a second. If you need to plug them, if you want to plug them all in before I move on, it's a good time right now just to pause it. Get the 0.2, the 0.3. Make sure you're getting both of the correct values for delta x and delta y and dy. Okay, now assume that's done. I'm going to go back and show something here. Remember my favorite graph that I'm going to keep going back to. Okay, this one right here. Remember what we're talking about. There's two different things. You have a secant line, which this is our main point right here, this x. Okay, we can go find some other x point over here. So we move over by delta x or dx, and then we can connect the dots, get a secant line, get the slope of that, get all the information about that. Okay, so just talking about that green secant line, we have a delta x and a dx, a delta x, which is this. We have a delta y, which is the change in y. Okay, the tangent line, the red one, remember the problem is there is no other point. You're not actually using another point. You're just going tangent to the curve. So you still have that point there. Your your dx is what you use to measure over as far as you want. But your dy, instead of going to this point up here, it's going to the tangent line. That's why it's differing. Okay, so what I want you to see is, we did this the other day, as delta x gets tinier and tinier, so as I start moving this in, watch what's going to happen. Now I get another point over here, I get another secant line, and you see how the slope's getting closer. We talked about that last week, but what I want to show you is your dx, your dy and your delta y. Here's delta y, here's dy, And you see how there was this big gap earlier? Now the gap's not as big. And as I get closer and closer, the gap between dy and delta y gets tinier and tinier. That was the thing they were saying. As delta x gets smaller and smaller, what's happening is this gap right here, that's the difference between delta y and dy, that's getting smaller and smaller and smaller. And remember though, as delta x gets tinier, the gap between these other two gets smaller and smaller. So now go back to that table that we just did on the example, and you see that they're trying to make the point, and it would have been better, I'll tell you, if we started at 0.3. So look at this delta x. Notice as delta x gets smaller and smaller, 0.3 to 0.2 to 0.1, getting small, look at the difference between these three things. See, here the difference is 0.9. Here the difference is 0.4. Here the difference is 0.1. You guys see how as delta x gets smaller and smaller, these two things become equal. Earlier, remember, you had that symbol right there. They're close as delta x gets tinier. So the smaller you make delta x, the closer those become, and they essentially become the same number. Okay, so that's the goal here of this example, is to try to demonstrate that. Okay, so we have one little word problem here. Company manufactures and sells X transistor radios per week. Here's the cost, here's the revenue equations, which we've used many times. And note, always know what your letters stand for. C of X, this equals the cost. So if I plug in X, I get the cost. R of X is the revenue. If I plug in X to this function, I get the total revenue. And what's X mean? Make sure you always know what X is. That's the number of transistor radios. So as long as it's between 0 and 8,000, this is what we use. So they want you to use differentials to approximate the changes in revenue and profit if production is increased from 2000 to 2010. Okay, so first thing, they want to get profit. Now they didn't really say this, but they want you to see what's going to happen with the profit if your production is increased. So remember, profit is revenue minus cost. So it's 8x minus 1,000, x squared over 1,000 minus 5,000. Now, I want to make sure everyone sees how in the world did they get this? Okay, well, look at this right here. This is r of x, 10x minus x squared over 1,000. C of x is this. It's, 5,000. I'm going to make sure I write it in the same order. 5,000 plus 2x. And remember, you're subtracting the cost, so you subtract everything. So what that gives you is this. When I subtract or distribute that negative, I get negative 5,000 minus 2x. And what they did here, they didn't show all this work, but they took this 10x and this negative 2x. That's how they got the 8x right here. The negative x squared over 1,000 is right there, and the 5,000 is right there. They just combined the two functions together and simplified it. So again, if you're not sure, pause the video, look at this, make sure you understand where I'm getting this from, and then unpause. Okay, so now this is the profit, and they want to see the change in revenue, which is dr. Okay, so what's the actual change of revenue? dr. So remember our formula. dr equals the derivative of it times the dx. Right? So, not that, sorry. So we find the derivative of the revenue, where are we at? Sorry, the revenue function right up here on top. Okay, so that derivative is this right here. And if you need to see it, this is what I like to do to make sure. Oh, let me give myself some more room here. This is the original function right here, r of x. 10x minus x squared over 1,000. Now I'm going to rewrite, because remember you want to have, I don't have to rewrite this, let me go back. Don't need to rewrite because we see it. Let me just do this. Maybe this will help some of you. But that's all you have right there. Oh, forgot my x. Okay, now I'm going to do the actual derivative. So notice here's where the prime r prime x comes in. That's a 10. And this one, bring the power up front, multiply to that, drop the power of the x squared by 1. So we get a 10, we get an x, there's nothing above the x right there, sorry, that's not a square, that's just an x. And then the 2 over 1,000 is where we get this 1 over 500. So just to show you where they got that from. So same thing like as we're doing these more and more, you should be not afraid to pause this video. Go ahead and pause it, look it over, make sure you're clear how we got this, then unpause. Okay, so now we have the derivative which we replace with r prime of x. And now look at what they've replaced. They took the dx and they put a 10 in there. I want to see if you can understand where that came from. So here's where it is. Remember, this is x1. This is x2. So the difference between them, delta x or dx, they're both the same. It's x2 minus x1, which is 2010 minus 2000. That's where this 10 comes in right here. Okay? Then this x right here, this is where it gets a little confusing. The 10 is dx. The x, we have to figure out, well, which one do we use? Do we use the 2000 or do we use the 2010? In these cases, you're going to do the first one because you're trying to figure out what's the change from the beginning. So this is the first x. It may not say that in the formula, but that's what you have to go with. Just like that graph I had, I keep going back to with that parabola. You're starting with one point and you're using another point to figure out the change. Well, what's our first point? Our initial, our first starting value for the transistor radios, it's 2000. So you plug in the 2000 right there. 10 minus 2000 over 500, that's going to be a 4. 10 minus 4 is 4 or 6. 6 times 10 is 60. That's the actual change in revenue, your DR. Okay? So if you look at what happened in this, now so far that's our change in revenue. We didn't have to do anything with this profit formula yet. Okay? They only asked in the first part what was the change in revenue. That's how we do it. Now we're going to find out the second part is what's going to be the change in profit. So change in profit is dP, which means you go to this profit equation. But the nice thing is it's just like the same equation over here. dP is the profit function, the derivative of that, times dx. Now we already found the d of x is 10. We have to find this derivative. So I take this entire thing right here. Let's find the derivative. Well, the derivative of 8x is 8. That's this one. The derivative of the negative x squared over 1,000, we did that earlier. It's still x over 500. And then the derivative of negative 5,000, any constant is 0. You just throw away the constants. So now I replace the x with the 2,000 again. I replace the dx with the 10. And you see we get this. 8 minus 2,000 over 500 is 8 minus 4. 4 times 10 is 40. That's our change in profit. So our revenue went up $60 when we increased it by 10. Our profit, went up by 40. Okay, so that's that part right there. Now let's look at some homework problems here. Okay, so as you can see here, I'm at my Math Lab page, going to our assignments. We are doing section 2.6 today in this video, so I'm going to go to this 2.5, homework number 5, 2.5, and 2.6, the second half of it. And you kind of remember from last time, we did a good chunk of these, so I'm going to pick right up at number 39. Continue my trend of just doing kind of every fourth problem. Okay, so give ourselves lots of room here, and they want us to, given the function g of x equals 4x minus 2, find g of 1.5. So you'll find this was kind of very easy to do, but got to make sure you guys are clear on it and you know what's going on. You're just going to plug in 1.5 to that function right there. So I'm going to take 4 times 1.5, and I get a 6, minus 2 from that, and I'm getting a 4. That's all they want you to find there. Okay, nothing special. Some of these, like I said, they're going to throw you these softballs in the beginning just to kind of get you reacquainted with everything that you've done before. Okay? Now we get to the ones that matter a little bit more. You have a function, f of x equals 5x to the third. All right? Make this a little bit larger for you. Okay, f of x equals 5x to the third. And like I said, I don't care for this having a triple type equation. Call it either y equals 5x to the third or f of x equals 5x to the third. Either way is good. Okay, so now we want to find delta x. So I'm gonna go back and give you my little cheat sheet. Remember this? Delta x, dx are the same thing. They're the gap between the two x values. Now, kind of put in here, this first x value is x1, that one is x2, and the difference between them, of course, is delta x. That's what they're having us find in this first problem is, what is the delta x? So you're going to take these two values, x2 minus x1, 4 minus 2, and you get your 2. Okay? Now, the other part is delta y. Once again, I'm going to keep pulling this back up. Remember, delta y is the actual change of your y values. So to find the delta y, we have to go, delta y, there you go, equals the change in the two y values. So actually plug them both in there and see what you get. So when I plug in 4 to this function right here, I get 5 times 4 to the third. Okay, 4 to the third is 64, so I think I have a 320 right here. Make sure you're getting that. Remember again, 4 to the third, 64 times 5, there's your 320. Okay? Now we plug in the value of 2. So this is going to be a 4 that I plug in right here. This is going to be the 2 I plug in right here. So into this original function, f of 2, we get 2 to the third, which is 8. 8 times 5 is 40. Looks like I have a change of 280. Now what's important also is make sure you get the sign right. Don't put a plus when it should be a minus or vice versa. Now we're going to do delta y over delta x. If you've gotten both of these correct, you're going to see 280 over 2. All you do is take these numbers and divide them, and that's how we get our 140. Excuse me. Okay, so that's it for that particular first problem. Again, pause, look this over if you have any questions. Okay, so let's look at number, so that was 43, correct? Yeah. Let's look at number 47, just to make sure, again, there's no surprises when you guys are doing these homework problems. All right, so we have a function, y equals x squared times the parenthesis x minus x over 2. Once again, they want us to find d of y. Make sure you know what d of y is. This is talking about the tangent line right here. Okay, so do you remember your other formula here? We had that one that told us how to find d of y. Let me pull that slide up right there. Remember, d of y is the derivative times delta x. Okay, well, let's see what we can find here. So plug in that formula. Just write it on the screen so we're all seeing what I'm talking about. dy equals the derivative f of x times delta x. Well, either way, we got to go find the derivative of this first. All right? So what I'm going to do is I'm going to multiply everything out so that we can actually find the derivative. Remember, you want individual terms. You don't want parentheses of things multiplying together. Individual terms, all regular powers of x. So my y prime is going to be 16x minus 3/2 x squared. Again, pause. Make sure you're clear how I got this derivative. So my dy equals all that derivative, which is 16x minus 3/2 x squared times delta x. Okay, so now I got to plug this in here and see what we find. Okay, so we have 16x minus 3/2 x squared end of parenthesis times delta x. I know we got a delta in here somewhere. There's my delta x. See what we got. All right, now you look at what they got, and this is why I'm doing this, because I want you to see what happens. All right, they remind you of this, and this is where it's going to get a little complicated, because you're going to get all kinds of funky answers or different things in here. Make sure we've got these right. Okay, so read this for a second. See if you can figure out what it's supposed to be. Okay, so. And like I said, I wanted to put that up there. The only thing I would see different for now is, well, maybe they didn't want a delta x. They wanted a dx. We talked about those. They're the same thing. Is that going to be the difference in the problem? And you see, that's all it was. Okay, now there's always back and forth. You look in your book, you're going to see this. All right, this is the formula they gave us. How come it didn't work? Because sometimes they want the dx. Sometimes they want the delta x. In these cases, for the most part, when you have a dy, they want you to use the dx. If there was a delta y, you'd be using a delta x. Even though we know delta x and delta y are the same, see the difference? It's gonna affect your problem. So I just wanted you to kind of come across that, because these little nuances are going to come and mess you up a little bit. This is why we're doing them now. I want you to see me making these errors, and then I want you to see, in case it happens to you on the homework. And the bottom line is, let's try not to make them when the test comes around. Okay? Or so the quiz is what I mean. I apologize. So now let's look at this here. We have y equals all this. Same kind of thing. To find d of y, I want to get the derivative. Now I'm going to put a y prime, but it's the same as f prime of x. It's the derivative times the dx. Okay? So whether you use dx or dy or delta x, we've seen already, they're the same thing. And I'll point out your second slide here. There it is. See how they had the same formula? That one, that one. They're both dy times it equals a derivative. One's times delta x, one's times dx. It doesn't matter. Oops, sorry. Because they are equal to each other. Because they're the exact same thing. Okay? So, let me erase this, sorry. Okay, so now we go back to what we're trying to find here. We have to find the derivative first. Okay, when they tell you find dy, you use this formula that I got you right here, and now let's find the y prime. Now before I do that, just like before, because there's a fraction, I don't want to have a fraction. I can't take a derivative of a fraction, but I can split this into two fractions. And if you recall, my rule from the other day is, as long as there's only one term on the bottom, no adding or subtracting of another term, you can do this. So notice these first two steps were simply me rewriting the y. I did not find a derivative yet. I just found what y is. Now I'm finding the derivative. Well, the derivative of 7 is nothing, so that's gone. And over here I get negative 2 times 3, which gives me a negative 6. And remember, you're subtracting 1 from the power. That's why I'm now getting this x to the negative 3. So my derivative, simplified, becomes negative 6 over x cubed. That's what I'm going to put right here. Negative 6 over x cubed dx. Now another thing, when you see a dx, that does not cancel with a normal x. So don't look at this and say, oh, let's get rid of these x's. No. An x will cancel with an x, but a dx, you have to treat that like it's its own variable, a whole different variable. So this is what I'm going to now plug into this answer. And let's see how it works. Okay, so we have a negative 6 over x to the third dx, and we get our excellent there. Okay, so like always, look that over. Make sure you understand where I'm getting all this from. Pause if you need to, excuse me, look it over and for a couple more seconds or minutes here. All right, let's look at number 55. All right, so we have same kind of problem. They give you a function, they tell you that the x is 9, and they tell you delta x or dx is 0.21. So I'll tell you, this is going to be the same problem as before, might actually even be easier in a way. So d of y equals y prime dx. So like always, I got to go find the derivative. Well, I have 174 square root of x. 174 square root of x. Rewriting that, that means 174x to the 1/2. Okay, remember the definition. We dealt with one of these the other day. So now I find the derivative. I take 1/2 times the 174, and then x is going to be 1/2 minus 1. Same rule as always. You're subtracting 1 from the power. So now I'm cleaning up a bit. I think 174 over 1/2 is going to be an 87, x to the negative 1/2, and y prime is going to be 87 over x to the 1/2, or 87 over the square root of x. So that's what I'm going to put in here, 87 over the square root of x. And then times dx. Now in the last couple problems, this is it. This is done. This is what I plug in, but they gave us more information. Now they told us that you can plug in a 9 for x. You can plug in a 0.21 for the dx, and now we can get an answer for this. Okay, you have to use your calculator, obviously. So we get a... All right, let's go over here. 87 divided by square root of 9, which is 3. So we get 87 divided by 3. That's our 29. We're going to multiply that by 0.21, and we get 6.09. And there's our answer for number 55. Again, pause it if you need to look over any of this. I will clear it and move on to the next one. All right, let's see what number 59 is talking about. Shape of a colony of bacteria on a petri dish is circular. Find the approximate increase in its area if its radius increases from 20 millimeters to 28 millimeters. Recall that the area of a circle is A equals pi r squared. All right, so they want the approximate increase. So what are we going to do here? Okay, so let's do this. How much is something actually increasing? That's the question we're looking for. So let me do a couple things. Area equals pi r squared. Okay, we're going from 20 to 28. Let me just show you a couple things here. If we were at 20, we would go from an area of 400 pi. If we were at 28, we'd plug that into that formula. We get A equals pi times 28. And then, of course, square both of these. You have to know what your 28 square is. Now, did you memorize all these? Probably not. Don't worry about that. You have a calculator. So we're going to take 28, square that. We get our 784 pi. So you all see here at least the actual change was 384 pi. That's the change, the increase. Okay, we subtract the two areas. We figured out the original area. We figured out the new area. We subtracted them. We get 384 pi. Now, I'm going to show you on purpose, if I plug that in there, is it going to work? So if I plug in 384 times pi, and they tell you it's not correct. Now I'll talk about why in a second. And they give you this hint right here. Okay, now I got a bunch of writing here, but they give you this hint, so use this. Like I said, I'm purposely going to do a couple of these wrong because I want you to see the feedback when you get them wrong. Don't treat it like you failed here. Just look at it as, okay, they're giving me a hint, and I'll show you a couple things. So I plugged in the pi. Well, maybe they didn't like the pi. Maybe I need to use my calculator. Okay, now I don't want to get too many wrong because it's going to make the problem start over. But let's say I did 384 times pi, and I get this. Okay, they just wanted me to use that. Let's just pretend that was my my theory. They wanted me to plug in this 1206.37 because I went to the 2 decimal places, but you're going to see, same thing, I'm getting it wrong. Now think about if you know why it's not correct. Here's the reason. They want you to find the approximate increase, okay? They want to know what's not the actual increase, but what's the approximate increase. So where's my special slide that I want to show you? Remember this over here? The actual increase is delta y. The approximate increase is the dy. We found the actual, the delta y. By plugging in the 2 values, subtracting the y's, that's how you get delta y. They want the d of y. That's the thing they're trying to ask. Now, of course, it's not d of y, it's d of a. This is what they want you to find. So remember that formula? We used a few times here. Let me show it to you. That one right there. dy equals the derivative times the delta x. It's the same thing here. Instead of y, it's an a. So the d of a is going to be the derivative of whatever that function is, that one, times, and it's not delta x, it's delta r, or dr, or delta r, because they're both the same thing. Now that's the one thing I know is, if this is my r1 and this is my r2, I can look at that and say, well, just subtracting those, I know that delta r equals 8, or dr equals 8. That's how much it differed. So I've got this part okay. That's not a big deal. But I need to go find the derivative. So all of this stuff, I need to hold back. This is giving me actual information. Now, in real life, people are wondering, well, why would you care about the approximate when you have the original? And that's a correct, astute observation. It's just getting you ready for the fact that in the future, you will not know the actual, and you're only going to be able to find the approximate. You'll always be able to find this approximate with this formula on the left. You won't be able to get actual if the data hasn't happened yet. You know, if we're talking so many years or months in advance, you can only predict it and you can model it. That's why I want you to see the connection of what it is. So as time goes out further, it's just an approximation, and they want you to find the approximation here. So look at this right here. Now this one's a little weird one. We haven't done one like this, but we're going to do it right now. I want to find the derivative of the a prime. It's easy. Just think about r as your variable. You do the same rules. Remember, pi is a constant. It's 3.14 always. I take the 2, I put it out front, and I subtract 1 from the power, 2 minus 1, like every derivative we've done before. And a prime is 2 pi r. So that's what I'm putting in right here. Sorry, don't make that look like a delta. That's a dA. We have a 2 pi r. Delta r. So now we plug in the r, and remember, we always plug in that first r value, that 20, and now we plug in the dr, which we found, which is 8, and we get, let's see here, 16,320 pi. Now remember the answer I was plugging in earlier, I think it was it 340 pi? That was the real change. This is the actual change. Now, one thing I'm not sure of is, are they going to want it as a pi, or are they going to want it as a decimal? Now it says round to 2 decimal places, so I'm going to go right to that. I don't know if the pi is going to work. Let me just do the pi and see what we get. So, if I plug in 320 pi, my math brain says that should be good enough, but let's see. Okay, they wanted this 1031, so we learned from this. If I was to instead, so this is what you don't do on your homework or your quiz. Let's go. We know it's 320. Let's take 320 times pi. And you see we get this 1000.3096. That's the answer they wanted right there. So a mathematician is going to tell you we want you to not go to decimal and give it as a pi. But in a class like this, because we're talking to actual business applications and real life examples, people don't speak in terms of 320 pi. They want the decimal. So we had the right answer. We just didn't have it in the right format. And I kind of knew that going in just because it said 2 decimals. I was just testing it right here to see. So at least we know what we need to do in the future when you see this number 59. And hopefully you've seen this on your homework. When you get it wrong, they'll give you a whole new problem and you can do the same thing. Okay, and I'll do this real quick just because we need this. A equals pi r squared. We're looking for dA. Remember, it's A prime dr, same formula. So my A prime, we did that earlier as well as this. So right here, I know that the dr is 2. That's all we're changing. So I plug in the 2 pi r dr, and r is the first value, which is the 40. dr is 2, and it looks like our change, our approximate change, is going to be I'm not getting this right. Sorry, 160. That's what I'm missing. Okay. So 160 pi, I'm going to take that in my calculator. And now that we know, don't use pi, use the actual decimal approximation of pi. 160 times pi gives me 502.65. And let's hope that one's better, and now we have it. Okay? So that's it for that one. That's all we need to do. So get a couple of these like this on the homework. Just want to make sure you're clear. You have no questions, no issues on these, but you should be good to go. This one I don't think is as bad of a section as some of the other ones that we've had. But kind of pulling up, where is my homework? There it is. Sorry, I wanted to show you the actual assignment list. Okay, regardless, that's it for this one. You should be able to do all the homework for week number 5, homework number 5 now. So if you have any concerns, like always, shoot me an email. Oh, here's what I was looking for. Yeah, we've kind of covered them all. Take this quiz. I don't think, once you get through section 2.5, I believe 2.6 is a lot easier. There's a couple little nuances we talked about today, but overall, I think it's better. As soon as you're good with this homework, start looking at this quiz number 5, and then get an early look at homework 6 if you want to. So I will record a couple more videos, send them to you over the weekend, early next week, and you're good for week number 5 now. So get that quiz in, get the homework done, and I will talk to you next time. Have a good one.